Let's start off by recalling the definition of cosine and sine. So, if you take any number, theta, thought of as an angle, we know that represents some position on the unit circle centered at the origin in the xy plane. So the basic idea is, as the drawing shows, if you take a line out from the origin, starting at the positive x-axis, the angle given by theta, or the position given by theta, is when you wind around counterclockwise if theta is positive, or clockwise if theta is negative, winding around in radians and eventually stopping when you get to your angle theta. So for example, if the angle was pi over 2, you would wind around pi over 2 until you would get to this position at the top. If the angle was pi, you'd wind around to here. If the angle was 3 pi over 2, you'd be down here. If the angle was 2 pi, you'd all the way back at the beginning. And if the angle was, let's say, 3 pi, well, you'd have wound around once, and then you'd go again until you hit here. So 3 pi all the way around. Now, the definition of cosine and sine is whatever position you have there given by the angle theta, it has an x and a y coordinate. Cosine of theta, by definition, is the x coordinate. Sine of theta, by definition, is the y coordinate. So that is the meaning of cos theta and sine theta. Okay, so first of all, I want to say a few things about this position P in theta. Now, it's a little bit confusing because different thetas will give you potentially the same point. For example, I have my theta there, that position P, and if I was to add 2 pi to it, I would wind all the way around again and end up at the same position. So different thetas can give the same point. Okay, so let's make sure that's kind of clear. So different thetas can give same P. So just as an example, I don't know, if I had pi over 2, so that's going to give me the very top of the circle. If I added 2 pi to that, that would give me 5 pi over 2. That has to give the same position. So the pi over 2 would start off up the top here, but then if I add a 2 pi to it to get 5 pi over 2, I'd wind all the way around and end up back at this position. Okay, so this, first of all, I suppose, in terms of functions, is going to tell you cos and sine are most definitely not one-to-one. There's going to be tons of repetition. So what I'm going to start off doing is trying to graph cosine and sine. And we're going to do it really, really carefully, bearing in mind what the definition is. So let's take this picture and try to kind of really slowly go through what it means. So let's think about graphing stuff. So graphs. So let me maybe change the coloring a little bit just so that it's easy to follow what corresponds to what. So let's have cosine in, shall we do green? And let's do sine in magenta. Okay. So what I need to do basically is to write down a graph, and for cosine it would be theta versus the x coordinate, and for sine it would be theta versus the y coordinate, because remember that's what they're doing. So let's start off with cosine, shall we? So cosine is going to be us thinking about the x coordinate. So let's do this pretty carefully. So I'm going to take an xy that I've already drawn, just so we have a grid on it to make sure it's really clear what everything means. So let's label my axes. So first of all, the independent variable is what the independent variable is theta. That's kind of what's going into the function. Now what's going out of the function? Well, let's use x as the output here. Rather than writing y, let's use x. And we're going to do that because I'm thinking about the x coordinate of this position P. So it makes sense to write this. Okay, so now let's label some of these positions. So I've drawn all of these vertical and horizontal lines. Let me kind of label some positions. So let's have this position as pi over 2. That's going to be an important position. Let's have this position as pi. Then let's have this position as 3 pi over 2. And then let's have this position as 2 pi, shall we? And in the negative direction, it'll be exactly the same. But let's just stick with this for a second, shall we? Okay, so what else? Well, let's label the top horizontal line as 1 and the bottom one as -1. Now, that's sensible because let's take a look at the P. The position P is what? Well, it's a position on the unit circle. So the x-coordinate is definitely between 1 and -1. It can't get any bigger or can't go outside of that interval, essentially. So it makes sense to have these kind of horizontal lines, 1 and -1, which are going to bound whatever's going to happen. So let's start off by kind of just marking some key points. If P is equal to 0, if theta is equal to 0, let's think about my position. So if theta is equal to 0, I'd be at that position there. And that has x-coordinate 1. So let's mark that on my graph. So it'll be this position here. Now at pi over 2, that's here, that has x-coordinate 0. So at pi over 2 is going to be at 0. So it'll be there. At pi, I'm here. Well, that's x-coordinate -1. So I would be down here. Where am I? At 3 pi over 2, I'm down here. Well, 3 pi over 2 then has x-coordinate 0. So x-coordinate 0, so you're back here. And at pi over 2, what happens? Well, at pi over 2, I would need to be back at my original position, which is here. That's x-coordinate 1. So I'm here. So how do you fill in between these? Well, as you move between these, you kind of continuously move. So let's just think about what the x-coordinate's going to do. It'll start off at 1. It'll start off at 1 here. And then as theta gets bigger, the x-coordinate will move along until pi over 2 and it's here. Then it'll end up at -1 here when we've done half revolution at pi. Then it'll start to move back until you're at 3 pi over 2, and then it'll move back here. So kind of the x-coordinate is kind of going to wobble back and forth like this, like kind of like a wave really, or something like that, right? Some sort of oscillating motion. So that means you've got this really nice looking graph. You kind of go down like this to there, to this position, up to this position, and then back up to here. So that's me carefully graphing what happens between 0 and 2 pi. But the thing is, what about all the other positions? Well, it's just going to repeat itself essentially. So for example, if I was going to, let's just do a few more. Let's do minus pi over 2, for example. So minus pi over 2 would correspond to this position here. Minus pi over 2, that's x-coordinate 0, isn't it? So I would end up here. If I did minus pi, well, minus pi is the same position as pi, isn't it? Right? Because you end up here. You just wind around this way. So again, that's -1. So you're back here. So what's actually going to happen is it's going to repeat itself, which isn't surprising because you end up back at the same location. So it's going to look like this. So this is me graphing, and I'll write it as follows. X is equal to cos of theta. It's kind of sensible to write x is equal to cos of theta because we're measuring the x coordinate, so it's a nice thing to have. So that's what cos of theta looks like. And you can see why this would be such an important function, because it's visibly a wave. And we are surrounded by natural phenomena which oscillate. I mean, literally take a wave, right? Going in and out, in and out. up and down, up and down. So the reason trigonometric functions are so important is because they have this wave-like property to them. It makes them supremely powerful when trying to apply mathematics to nature. Let's do sine and see what happens. So it's going to be a very similar story. But now instead of the x-coordinate, we do the y-coordinate, aren't we? Because that's what sine is. So we're going to do the y-coordinate. So same basic story. Let me go down and grab this again. So we'll use exactly the same scale as above. So what have I got? So let's now do, okay, so let's label our axes. Theta again is the independent, and let's do y as the dependent. Makes a lot of sense because of the fact you are measuring the y-coordinate. Okay, so let's go through it. What happens if theta is equal to 0? Well, theta is equal to 0 is this position. The y-coordinate there is 0. So that means I'm going to start at 0 here. So again, what about pi over 2? Well, pi over 2 is up here. Now it's not the x-coordinate, remember, it's the y-coordinate. The y-coordinate there is 1. So it's going to go up to here. Same scale exactly. At pi, I'm here. So there, the y-coordinate's 0. So now at 3 pi over 2, you're there. That y-coordinate is minus 1, so I would be down here. And then finally, when I'm back at 2 pi, I'm back here. So that's y-coordinate 0 again, isn't it? So now what's going to happen is as I move, if I'm just looking at the y-coordinate, I'm going to start here, I'm going to move up to here, and then down to here, and then back to here, and I'm going to oscillate like this. So this is a really important way to think about these, is kind of oscillating back and forth between these two extremes. So again, that means when I graph this and join these points, it looks like this. So you're going to rise up, then you rise, oh sorry, you go down. Same story here. And you're going to go back up to this. And just like before, it repeats. So it's the same thing kind of in blocks. So I won't go through every single special value here, but it's the same exact idea. Very nice. So this is now y is equal to sine of theta. So very, very similar looking. Very, very similar looking. And yes, as I said, you can really see why these are such important functions, because they're waves. And like I said, waves are important things in nature. So it's exactly the same scale. I'm just going to write it in just for completeness. So very nice. So that's us really carefully going through the construction of the graphs of cosine and sine using the definition, right? Using the fact that the x-coordinate is going to oscillate back and forth like this, and the y-coordinate is going to oscillate back and forth like this. And we're just measuring that. Really lovely. Now, I look at these, and there's something about these graphs which is very different than all the other graphs I saw before. Namely, or in all my other core examples, namely, they seem to be repeating themselves. So let's single out a property which means a function repeats itself. So this is a property I could have given, I suppose, in properties, or the basic properties of functions videos, but I think it's better to have it here because it really only turns up for trigonometric functions. So this is called periodicity. It's a fancy word. Periodicity. So definition, let me just jump straight in and tell you what I mean. Definition, given some positive constant, a positive constant, a function f is So this is kind of omega, little omega, omega periodic. If the following is true, if when I take my input and I add any integer multiple of omega, it doesn't affect it. Okay, so this is for all x in the domain. So let me just say a quick word about this. This is a bit of a scary looking definition, I think, the first time you see it. It's not so easy to wrap your head around what this k omega business is. First of all, what does k mean? K is any integer. So any whole number, positive, negative, 0. Any integer. So e.g., obviously 0, -1, -5, 7, ... Right, let me show you a picture of what this actually means. So a picture. So let's move this out of the way because I think we may need it in a bit. Right, so let me imagine I have a graph. So we'll do x, we'll do y. And let's imagine this is where my omega is. Okay, so let's imagine this is what my graph looks like between 0 and omega. That's a really, really bad graph. So we'll take that, right? So that's what it's like between 0 and omega. This statement is a fancy way of saying it's got to repeat over and over again like that, like a heartbeat or something like this. So it has to look like this. So it's got to be exactly the same over and over again. ... So this is what it means to be omega periodic. It means it's going to repeat in blocks of length omega. So this is me graphing some example, which is omega periodic. And the key thing is, if you draw any, and you can do it anywhere really, but if you draw any interval of length omega, it's going to repeat in blocks like that. So this k business is just me saying it's the same over and again. So if I was, for example, to choose this position, I'll do it in grey. If this was my position x, okay, well, x plus omega would be this position here. X minus omega would be this position here. X minus 2 omega would be this position here. And all of these positions are exactly the same value, aren't they? Right? They're all kind of like this guy. So that's why this k business is turning up, because you're repeating every omega. Omega, 2 omega, 3 omega, and then in the negative direction as well. So the reason I'm isolating this property is because it's very obvious that these guys satisfy that property. They are repeating in blocks, aren't they? So because of the fact, so again, let's give ourselves a little bit more room with this. So because theta plus 2 pi, theta minus 2 pi, theta plus 2 pi times 2, theta minus 2 pi times 2, all of these give the same position. That's the same p. All give the same point on the unit circle, because they're all full revolutions, right? Plus 2 pi just says we'll just go all the way around and end up back at the same position. going counterclockwise. Minus 2 pi is you do the same thing but in the clockwise direction. They all give the same point on the unit circle. What does that mean? Well, it means if I was to write cosine of theta plus, how will I write this? 2 pi times k. That's always equal to cos of theta, right? Where k here is any integer. Because all this is doing is just winding around a full revolution, either clockwise or counterclockwise. And you're doing it a few times. So if k was 5, this would be doing 5 full revolutions counterclockwise. You'd end up at the same position, so it would be the same x-coordinate. So it's true, of course, of cos, and it must be true of sine. Because the y-coordinate is going to be the same. So, as I just said, this k, it corresponds to a kind of a full revolution, either clockwise or anti-clockwise, or maybe this corresponds to k full revolutions. That's what I should really say. So this corresponds to k full revolutions. And if k is positive, it's k full revolutions in the counterclockwise direction. If it's negative, it would be in the negative, or the clockwise direction. So what does this mean? This literally is the statement that you are 2 pi periodic. But let's draw a picture to illustrate why this is true. So let's take both of these guys and bring them down. So visually, what this is saying is, can I get them both on? Yeah. What's it saying? Well, let's kind of remove some of these lines. We don't really need them anymore. They were good guidelines before. What this is saying is I'm repeating myself in blocks of length 2 pi. And you can see that exact thing going on here, right? For example, this guy, if you take any block of length 2 pi, but this one, for example, that's like your omega. You're repeating in a block of that length. And same thing down here. You're repeating in a block. So this is something very special about these functions. Basically, none of our other core functions do this, and this is the reason these are so useful. So what's the conclusion? Both of these guys, all of this together, is really telling me that sine and cosine they're 2 pi periodic, is what we'll say. They repeat in blocks of 2 pi. Okay, so let's do an example which is easy to get confused about. So if sine and cosine are 2 pi periodic, what happens when I transform them a little bit? So here's a really nice example. This is kind of a challenging example based on this. So a challenging example. So show that fx equals sine of 2x is pi periodic. So not just 2 pi, it repeats in faster blocks. So there are two ways to do this. The really proper way is the algebraic way to check the condition of being pi periodic. So to add integer multiples of pi and see that nothing changes. But let's do it graphically. Let's think about what the graph looks like. So graphically, so this isn't really mathematically rigorous, but it's a very useful thing to do. So we know what the graph of sine x is, right? It's this guy above. So what's the graph of sine 2x? Well, we know what that transformation is. It's going to compress horizontally by factor 2. So if I take this with the same scale as usual, then what's it going to look like? Well, it's basically going to go through this wave, but twice as fast. So what you'd end up with would be this, I think. Let me write this a bit better. So let me label everything. This is pi over 2. Make it a bit smaller. And this is pi. So it's basically run through the wave twice as fast. So if I was to graph this or repeat it, so let's just do that. Nice, it would just be the same thing repeated in each direction. So it's the same basic story, it's just happening twice as quickly. Neat. And I can kind of visibly see here that it's going to repeat in a block of length pi. It's going to repeat in a block of length pi. So this again is a horizontal compression. So this is y is equal to. So I should label everything, shouldn't I? I should label everything. Let's label it. In fact, let's not do 2x, let's do 2 theta. Because I'd never used x for it, did I? Because it's a bit confusing at this stage. It's perfectly fine to use x. But it's nice to have theta just to really hammer home the point the independent variable should be thought of as an angle. So I'll have a y here. So this is y is equal to sine of 2 theta. So again, what we're really doing here is a horizontal compression by factor 2. From our transformations of functions. Horizontal compression by 2. So that's kind of a visual way to see it, but let's do it actually really properly to completely certainly verify it. So here's the algebraic way to do it. And I think this is kind of more precise, more mathematically rigorous. So drawing a picture is all well and good, and it's an important thing to be able to do, but it doesn't prove with absolute certainty something's true, right? It's like if you're talking about a function being odd or even, you can draw a picture and say, look, it appears to be symmetric in some way. That's great, but if you want to absolutely know, you need to check the conditions. You need to check the defining property. For example, if you're even, that f of minus x is equal to x. So you've got to check that. It's no good just appealing to a picture, not to do it really rigorously. So let's do this. F of theta plus, let's say, k pi. So what's this equal to? This is equal to sine of 2. So remember, this is the input, so that's going to go directly for the theta. So this is theta plus k pi. But then I'm going to distribute sine 2 theta plus 2k pi. But now sine itself is 2 pi periodic, and all I'm doing is adding a multiple of 2 pi here, an integer multiple of 2 pi. So this has to be equal to what? Sine of 2 theta, which is equal to f of theta. So this again is because sine itself, so adding something to an input to sine, which is an integer multiple of 2 pi, doesn't change anything. So sine is 2 pi periodic. That's what we're using here. So this is kind of two approaches to the same thing. The graphical one is very nice, but not mathematically completely airtight. The algebraic one is completely solid, but a little bit more opaque, I think. So finally, just a useful fact, one that you might want to check yourself. This is part of a kind of a more general story about how certain transformations affect periodicity. So here's a useful fact. So if f of x is omega periodic, so it repeats in blocks of omega, then if you transform it as f of c times x, where c is a non-zero constant, so c strictly bigger than naught, let's say, then this is omega divided by c periodic. That's a nice exercise for you to check. Does that fit what we've just done? Well, absolutely, because sine is 2 pi periodic, and sine of 2 theta is 2 pi divided by 2, so pi periodic. So this is kind of a nice general principle about how this transformation affects periodicity. And it's not hard to see why, because the transformation is horizontally stretching or compressing, depending if c is greater than 1 or less than 1. So that has the effect of kind of increasing or decreasing the block which you repeat in. So just to summarize everything again, the definition of sine and cos is the x and y coordinates on the unit circle of the position given by the angle theta, according to the recipe we've discussed at length. If I graph them, they both look like waves, essentially. And waves are things which repeat themselves. That's one of the core properties of these graphs. And we've introduced the idea of periodicity, which is the idea that you repeat in some fixed block of length omega, let's say here. And sine and cosine do that with blocks of length 2 pi. And if you mess with them a little bit by, well, scaling the input by 2, that will half the periodicity in this example. So next time we're going to look at other properties of these functions.